All right, so hello everyone, my name is Andrei Mihai, and I will be talking about using convolutional autoencoders for precipitation nowcasting based on radar data. So the goal of this part of the research, I just want to present the overview of what we did, is that we wanted to do some radar data prediction. So starting from radar data, we wanted to predict radar data. More exactly, from the radar data gathered at one time step, we predict the radar data at the next time step. So from one step to another. So this is very short time forecasting. So it is weather nowcasting. We also wanted to do nowcasting as a classification. So predicting as classification, meaning that we predict whether the values at certain locations will be higher or lower than certain threshold. So instead of directly trying to predict the value, we will be trying to predict whether there will be the values at the future location will be higher or lower than a threshold. And we also wanted to create this classification, so to do this classification using a machine learning model based on autoencoders, which are a type of neural networks. So the radar data that we used from ANME, we used the data collected over the central Romania from a radar, well, so this is in Transylvania, from a radar near the village of Bohalma. The radar was this type of radar, a single polarization radar, weather surveillance radar. And this type of radar does a full volume scan every 6 minutes. From that volume scan, from all the products that the radar outputs, we only used for our AutoNowP experiments, we only used the base reflectivity product. So AutoNowP is the name of our model that we created with autoencoders. So we used only base reflectivity products. The base reflectivity estimates the size of water droplets, is expressed in dBz, decibels relative to the reflectivity factor Z. And as most base products from radar, the product is outputted on multiple elevation angles. So the radar outputs on multiple levels, and we only used the lowest elevation angle, only the lowest level of this product. So we only used one product, R01, from the lowest elevation angle. So this is the data model here with an example of how we wanted to use the data. Since we only use one product, we have one data grid or one data matrix. And this data matrix represents the output of the radar, which at one time step, the output of the radar at one time step, with every point in the matrix representing one location. So how we wanted to represent the data is that we wanted to have an instance at every location, at every point in the data, we have one instance. And for each instance, we have, for example, in this example, the instance at location 33 would be composed by the value at that location and its neighborhood. And then this will be the data. This smaller data grid will be the data for that instance, and this instance will have a label. So the label would be the value at that location in the next time step. So this is the time step at t-1, this is the time step at t. So this is the data that you have. We have a data grid for a neighborhood of a location with a label with the value at the next location, at the next time step at the same location. So this is the data model that we have, but we also have multiple instances. So we have an entire data set out of all these instances. We have one instance for every location, for every time step. How we pre-process this data? The main idea is that we separated in two classes. We have a positive class, instances having their label higher than a threshold, and the negative class, which is composed by instances having the label lower or equal to the threshold. So our data set is composed of two data sets, one with positive instances, one with negative instances. And the idea was to train the model to learn to separate between these two classes. Also, we did normalize our the data in our data set with the usual normalization formula that gets all the data between 0 and 1, depending on the minimum maximum of the values in the domain of the reflectivity of R01. So this is about the data that we had. Now we wanted to implement this using autoencoders. As I said, autoencoders are a type of deep neural networks. The main idea of them would be that they learn low-dimensional representation that capture relevant characteristics of the input data. So just as a short introduction to what autoencoders are, I have here a small graphic. The idea is that an autoencoder is a neural network where the input and output are the same. And usually the input is higher dimensional, and it has two parts. It has an encoder and decoder. So it does an encoding to a lower dimensional representation. Usually it is a lower dimensional representation, and then the second part does a decoding. So the autoencoder learns to encode and decode by having the input the same as the output. So this is during the training process. It tries to recreate the input while learning how to encode and decode from this lower dimensional representation. This is the main idea of what an autoencoder does. Now, of course, autoencoders have different kinds of uses in different kinds of problems, depending on whether you want to use this low representation or the encoder or the decoder or so on. But the use that you have for autoencoders, we are basing this on the supposition that the autoencoders are able to recreate properly input data that is similar to the data that they had during the training. So autoencoders are trained on a data set, right? And if you give an instance to an autoencoder as an input that is similar from to everything that it was in the training data set, then that instance will be able to be encoded and decoded properly. So the input reconstruction that the autoencoder outputs will be very similar to the actual input, right? Because it is very similar to what the autoencoder saw as training. On the other hand, we suppose that if you give to the autoencoder an instance that is very different from what it saw during the training, it will not be able to properly encode and decode this input reconstruction. Well, it won't be able to properly encode and decode, and the input reconstruction will be different from the actual input. And this is what we wanted to leverage, the fact that the input reconstruction will be or won't be similar to the actual input. And here is what we are trying to make the difference, but you'll see soon. We also wanted to use convolutional autoencoders. These are able to capture spatial patterns. We did this because, as I said, our representation is this small data grid that is the neighborhood of a location. And since every point here is a location, there might be some spatial patterns that can be learned. So that's why it is a better idea to use convolutional layers in our neural network. So here is the actual model for actual network architecture for our AutoNowP model. We have this. This is one autoencoder. This is the input needs to be the same as the output. Then you have the encoder part, which is created from 3 convolutional layers and then a dense layer. So this is the encoder. And then we have the decoder made by 3 conv2D transpose, which is basically just the reverse of a normal convolution. Now we also have this zero padding and cropping layers. This is because the convolutions, when especially the conv2D transpose, they just increase by double the size. and at the end they will be like powers of 2. But our neighborhood, it won't have necessarily power of 2. We had neighborhoods like it's dimension 7 or 13 or something like that. So you needed to make sure that the input and output of the convolutions are the proper size to be able to have good convolutional layers. So that's why we needed to do a zero padding at the beginning. And after the reconstruction of the convolutions, we needed to crop the extra part. So this is the architecture of a convolutional autoencoder. So actually we have two of these convolutional autoencoders. We have one autoencoder for each data set. So here is what I mean. This is the overview of how this experiment works. The idea is that we have all of the data points and we separate them in the positive instances and negative instances. As I said before, we have the two data set, positive data set and negative data set. And then you have two convolutional autoencoders. All of them have this same, both of them have this same architecture. So the first convolutional autoencoder is trained only on the positive instances, and the second one is trained only on the negative instances. So you have like a positive autoencoder and a negative autoencoder, trained on the positive instances and the negative data set. So this is our idea, that this one on the positive instances will be able to recreate input data only if it's from the positive instances. If we give a negative instances after this one was trained, if we give a negative instance to this autoencoder, the output of the autoencoder won't be similar to the input. So it will not be able to reconstruct the input because the positive autoencoder was not trained on these instances. So since it won't be able to reconstruct the input, we will be able to tell if it's a positive class or not. So this is how the testing works. For a carry instance, we give that instance to the positive autoencoder and the negative autoencoder, and we compute the loss or the error of the input reconstruction. So if the error is very big for the positive autoencoder, that means that it's probably not a positive instance because the positive autoencoder did not create it correctly. And the same goes for the other autoencoder. This is the main idea of how this AutoNowP model works, with two autoencoders trained on their respective data sets. Now I want to talk a bit about the training loss function. Since so each autoencoder is trained, and here we use a slightly different training loss function for each of the autoencoders. We used a modify mean squared error. So we separated the mean squared error into mean squared error over greater and mean squared error lesser. So this is the mean squared error for the data that is greater than the threshold, and mean squared error lesser is the mean squared error for the data points that are lower or equal to the threshold. So the idea is that if we just sum these two mean squared error, greater and lesser, we would have the normal mean squared error. But we also added this alpha parameter here. And with this alpha parameter, if it's 0.5, it's the normal mean squared error because they have the same weight. But if you have alpha higher than 0.5, then it will have a greater weight for the data that is greater than the threshold. And you use alpha higher than 0.5 for the autoencoder that is trained on the positive instances. The idea is that this autoencoder should give more weight to reconstructing the input properly, especially for the elements that are higher than the threshold. And then the same thing was done for the negative, the autoencoder trained on the negative dataset. The alpha was lower than 0.5, meaning that the loss would put more weight on the points that are lesser or equal to the threshold. So the autoencoder will prioritize more the points that are lesser than or equal to the threshold. So this is what we used as a training loss function. Now, this is how we compute the probabilities and decide in testing which is what the carry instance is. So after the autoencoders were trained, we need to be able to test to see, okay, for one carry instance, we have one instance, is it in the positive class or the negative class? How do we do that classification? So we do that classification by getting that carry instance through each of these autoencoders and having the input reconstruction. And then we compare the input reconstruction to the actual input. And we compare that using mean squared error, the normal mean squared error this time. So here we have the mean squared error between the reconstruction for the negative autoencoder and the input, and then the mean squared error between the reconstruction for the positive autoencoder and the input. So the idea is that this is an error, right? So if the error is 0 for the reconstruction by the positive autoencoder, that means that the positive autoencoder was able to perfectly recreate that instance. So that means that it's much more probable that it is part of the positive data set if the autoencoder did such a good job, right? Without the error being 0. So this is why we have this formula here. When this error is 0, then this reduces to 1/2, so it will be in total a 1. And if these two are equal, then the probability will be 0.5. That means that's the error are the same for the two autoencoders. So the instance was at the very limit of the two classes. So then it's 50-50 if it's in whatever class. And then if the error is for the negative autoencoder is lower than this one, then the probability decreases below 0.5. So it's more probable that it is in the negative class. And if it is 0, when this error is 0, then this reduces to 0. So this is why you have this formula here for the probability computation. Okay, so our case study was done on radar data gathered from 20 days from June in 2010, 2017, 2018. So 20 days from summer, and they were chosen in such a way that there are several different kinds of weather events and weather data, and there might be either powerful weather events or calm days and so on. So a varied data set. As I said, we have one instance for every location at each time step, and we have over 200 time steps in every day. So then we have a lot of instances, over 9 million instances for this product of interest, reflectivity at the first elevation angle. So what I wanted to show you here is that it is a very imbalanced data set. The number of positive instances are only 3.44% of the total. So very few positive instances. It's a very imbalanced data set. So this shows that it is quite a hard classification problem. Also, this entropy shows it's another measure that can be used to see how imbalanced the data set is. And 0.2 means very low entropy, so that is very monotone data set with not many patterns in it. So that means it's quite a hard classification problem, especially because of balancing. Here are some of the metrics that we use. The first three are more important from a meteorological point of view, but we used multiple metrics to be able to properly measure our model from a computational point of view. And yeah, all of them are based on the confusion metrics. So here are the results. We used different thresholds, increasing from 10, 20, 30, so 10 dBz, 20 dBz, 30 dBz. And the idea here, you can see the results shown with 95% confidence interval. So the key takes are that in general, performance decreases when the threshold increases because the imbalance decreases. So this imbalance was with a threshold of 10. So with 20 or 30, this is so the threshold, as the threshold increases, that means that there are even fewer positive instances. So it makes sense that with such a big imbalance, with so few positive instances, the performance in most metrics will be very low. The exception is specificity and positive predictive value, which increases with the threshold. This is because these two metrics are heavily influenced by the false positive number. But the false positive number decreases because there are much fewer positive values in the first place. So it doesn't learn enough to give out false positives. So that's why positive predictive value and specificity actually increases. So the best, it does the best, it has the best values at threshold of 10. And we also compared the AutoNowP with other classifiers. And here are the results, again, with 95% confidence intervals. We compared it with more classical classifiers like logistic regression, linear support vector classifier, decision trees, or nearest centroid classification. And as you can see, while logistic regression and SBC have some good results, also in general, AutoNowP has the best results out of the other types of classifiers. Yeah, so this was my presentation. Thank you.